Okay, can you hear me? Genesis, can you hear me? Can you see me?
Yes, doctor.
Okay, thanks. Good morning. On Monday, we start describing Can you see my Word document?
Yes, doctor.
Okay, thanks. So we said that in the case of finite elements, we do a discretization. And this discretization, in the case of the finite element method, it has two phases. In the first one, we partition the domain. That means that, for example, if this is the problem that we want to solve, for example, this is a bin, right? The domain goes from 0 to L. This is a 1D problem. And what we do is we partition this domain. For example, in this case, we have partitioned in two parts, from here until half and from half to the end, two elements. So each one of these is a finite element. That's the first thing. And the second one is that in every element, we do an interpolation. Okay, so that means that immediately you think that if you have a problem, okay, if you have a problem, you know that the solution has a certain mathematical form. For example, the solution could be, I don't know, maybe quadratic or cubic or to the fourth power, right? What happens if you interpolate with the function which is different from the exact solution? And the answer is immediate. The problem is that there is going to be a difference, and that difference means error. Okay, so this interpolation tries to get close to the exact solution, but it's not exact. So we have to be aware that finite elements is not an exact procedure. It's a very good approximation, but it's not exact. Okay, so eventually we have to have in our mind the question, how good, how close is this answer, is this result from the exact one? Okay, before analyzing, it will insist on that. Now, for example, what would you do if you suspect that this solution that you obtain using finite elements is not good enough? Do you have any suggestions for that? Do you suspect that this interpolation is not good according to the loading that I am applying? What would you do? Somebody, anybody, what would you do?
We consider another element.
Exactly. So instead of using only two elements, I could use, for example, 4 elements. In that case, every element will be very small. So even though the interpolation is different than the exact solution, we can think that this strange solution can be approximated by small arcs of curve, right? So you can get closer to the exact solution, okay? And in this way, always you have to think or try to answer the question, this answer, these results that I am obtaining, are they close enough to the exact one? And the answer to that is the way that you just answered. Do another partition and compare. Okay, so if the differences between the results of these two partitions are small, then you can accept that this is a good approximation. If you find that doing this another partition, you obtain a large difference with the previous one, then you can expect that you still need to go on and do another partition until check that you are close enough. That means that you do 2 partitions and the results are very close between them. That means that you are very close to convergence. Okay, we're going to insist on that, but this is something that we have to have in our mind. Finite element is a very good process, it's a very good algorithm, but it's not exact. Okay, so we have to be aware of that. Okay, and this is the way we're going to work. Okay, we said, for example, in this case, it's a beam. Okay, we said, okay, if we knew for one joint, we knew the displacement and the rotation, and also for the other one, what we're going to do is for every element, we're going to set the displacement in this way. Is the product of these functions, which are completely known. This is completely known. We will see that. And multiplied by the joint displacements. So instead, yes?
There is a question from Alex Nevares.
Okay, let me complete this idea and I will go to your question. Thank you, thank you. So for every element, I do this. So instead of trying to find a continuous function for this, I'm trying to find 4 values for every element. So that's what we call a discretization. Okay, so at the end, you will see that the number of joints, in this case 3, multiplied by the number of degrees of freedom, in this case 2, because we want to know the displacement and the rotation, that will give us the number of degrees of freedom, total degrees of freedom that we have in our problem. In this case, would be 6. So instead of trying to find the function exact solution, we try to find 6 values. That's discrete number. Mr. Nevares, go on, please. Mr. Nevares?
Good morning. I have a question. You said that if we are not closer to the real answer, we may need more elements. But what if that is not the case? If in reality we have bad programming or bad code, how do I know that even though I
let me
more elements and more computer, but I don't get closer?
Yeah, I know.
How do I know if that is?
Let me try to answer that. Let's suppose that let's go back to this problem. Okay, it's a very simple one, but it's a good one. Okay, so we have this clamped on one side, and it's simply supported here, and I have a load here, something like that. Okay, let's suppose we do a first partition. So we have one joint here, another here, and another here. Okay, so this is element 1, and this is element 2. Okay? Now, let's suppose that we control the displacement here. Okay, let's call displacement of check. Why? Because probably this is going to be a good value, very important value for us, since in this point, I'm applying the load. So what we can do is this. Here, I have the total number of joints. In this case, I have 1, 2, 3. So I have 3 here. And let's suppose I'm going to plot on this scale the value of this displacement, which is the check. Okay, now the exact one, I don't know. Do you know that? No, nobody knows. So I'm going to write it like this, dotted. Why? Because nobody knows that value. So this is what they call it a star. Okay, now we do not know that. But we know that as we increase the number of joints, we're going to go like this. So when we use an infinite number of joints, we're going to go exactly in the value D star. So what do we do? we obtain a response, an answer for that, and we plot it here. But we know how far we are. What do? We do a second partition. So we have one join here, for example, one here, 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 and here. Now we have 5. So if we plot here, we're going to have like this. We solve this problem, and of course, we have a value for this check. So we're going to be here. And we notice that there is a difference, a good difference between this value and that value. So we can say that we are in this part of the curve, not in this part of the curve. Since we have a good difference here, what do we have to do? We have to increase the number of joins. So let's use this. We include another one. Oh, shoot. Let me change color. So we have another. Oh, man. Doesn't want to work. Another value here. Then use a triangle. Okay. Another value here, another here, another here, and there. So now I have 1, 2, 3, 4, 5, 5, 6, 7, and 8, I think, right? So I'm going to go like this. And now the value that I obtain solving this problem will be this one. And you see that if I go from here to there, this distance, this difference is this value. And I can go from 5 to 8, the difference is going to be this one. What can you say, Mr. Nevares, with these results?
That there is a limit for...
Yeah, we're closer. That's what we can say.
Yeah.
Because we go from here to there, we change something. If we go from here to there, of course we change it. But the change is much smaller than this one. So we can say that with 8 joints, we are very close. If you still want more, you can go on and use, for example, I don't know, maybe 15. And you will see that the difference between these two results will be even smaller. That means that you are very close. Okay? So when you have a very small change between 2 partitions, in one of the parameters, that means that you are close to being converged. Okay, this scheme that I'm showing here is something that we have always to do. And at the end of the semester, when I ask you to complete the project, this is something that you have to do. Okay, you have to do a partition of the domain, get some answers, and then do another partition and compare. If the responses are close one to another, that means that your final partition is adequate. If you find that the differences are very large, you have to decide what is large for you, then that means that you have to do another step. Okay? Nevares?
Yes.
Okay.
Doctor,
Yep.
there is another question from Jaime Zamora. He
Okay,
asked
go.
if you always try to make it coincide the force in the joint.
We will see that in a minute, but it is possible that you make a partition, and in that case, these external forces do not coincide with the joint. But the best to do it is, yes, make it to coincide. So you have a joint at the point where you are going to apply a force.
So in general, we try to make it coincide.
Yeah. We try to make it coincide. But you could analyze, for example, let me, this is an extreme. I don't suggest to do it, but you can do it. So you can analyze this partition. For example, let me go back a little bit. For example, I can have the same problem, okay? The same problem. But now I'm lazy. I don't want to have the time. So I'm put another one join here and another join here. And I can solve this problem. What happens is that what I do is I take this force and I convert that into equivalent forces here and here. But of course, you can easily imagine that the solution for this one will be very poor. So probably you will be done here. So the solution will be very poor, but you can do it. You can do it. So the answer. So the answer is yes. You can analyze these cases when you can see that the force, the applied force, does not coincide with the joint, but it is much better. Remember, this is an approximation. This is not exact. So you can get a better approximation when you include a joint at the point where you apply the force or a moment. Yes, another question?
Yeah, this is the same that we do when we have no equidistant forces, when they're...
Yeah, it's the same. For example, you could have, that's the beauty, or that is the force that we have with finite elements, that we have a lot of flexibility. For example, let's suppose I have to analyze this case. And instead of having here, I have the force here, like this. What I can do is I can partition this like this. I include one joint here, and one here. So this is element 1, and this is element 2. And obviously, the length of them is not the same.
The joint and the first element disappear. Yeah.
Sorry, here. Sorry. So in general, elements do not need to be of the same
length,
dimension. I use dimension because in general, I'm exemplifying with a beam, but we could also use plates. Okay? Okay, let me go on with these ideas, and then we're going to say something about modeling, see, because we never analyze an exact structure. We always do simplifications, and that simplifications is what we call modeling. And then I'm going to explain the general steps that we follow in the finite element method. Okay, I don't know if I have the time to start the next subchapter, which is related to bars. Okay, that's the simplest element, the bar. And at the end, I will try to leave some minutes in order to answer questions about the assignment if there is questions about it. Okay? Okay, so we have explained, we have shown here the case of the partition of a beam. Okay, in the case of plates, we can do something similar. So for example, we have a plate like this. Okay. In this case, of course, you can recognize easily that you have two dimensions. So what do? Exactly the same. We partition, but we have to recognize that the domain now has two dimensions. So the partition will be, for example, something like this. So we go like this and like this. Now that's the first step. But then we have to do an interpolation. So this is partition. This is partition. The domain. But now we can have to do an interpolation for every element. Now you can see immediately that this element is not a line. So you see here, in this case, we go from here to there. That's one element. In this case, this element is close to a rectangle. So you have two dimensions. Okay? So we can say that for every plane element. See? So we take each one of these and you see, okay, I'm sorry. Let me include here these points. These are the joints. In this case, we have 9 joints. Let me explain this only with the displacements. I'm not going to include the rotation because I can get into a very difficult situation for drawing. This is one element. For example, this is the ith element. Okay? Now, this element is defined by the 4 joints which are located on the corners. What do we do? Okay, if we try to find the displacement W, that depends on X and Y. Okay, what do we say? Okay, if I knew the displacement of this point, let's call this D1Z. If I knew the displacement of this joint, D2Z, this one here, D3Z, and this one here, D4Z. If I knew these 4 values, what we can do is we can set up an interpolation polynomial. Of course, the polynomial will depend on X and Y. But the most important part is that if we do this interpolation, we are going to have only how many unknowns, people? How many unknowns if we do an interpolation? How many unknowns?
4.
4. That's 4. It's a discrete value. Let me try to see. I have to go from here to here to here and to here. Let's try. So I go like this. You can do a better job in your class notes. Like this. Like this. And like, oh shoot. We have to start here and we have to end down here. And then of course, in between, we go like this. Like this. I'm not going to draw the whole thing, okay? So you can do better at home. Like this. Like this. So this blue function, it's an approximation. We say this W is not exact, it's an approximation. And that depends on X and Y. And in a similar way as we did before, let me go back to show you. Here, in this case, you can see here that we have, these are the unknowns, and these functions are polynomial for interpolation. The difference is that in this case, in this example, I depend only on X. In this sample that I'm showing here, in the next page, we have dependence on X and Y. So we can say here is that we have a row multiplied by a vector. Okay, here we have, this is D1Z, D2Z, D3Z, and D4Z. And each one of these are multiplied by a polynomial. In this case, it's going to be P, let's call it P1, which depends on X and Y. P2, which depends on X and Y. I'm not going to write that, and you can imagine what you can find here. So the most important part here is what? Is that this part, the polynomials, are known. These are known polynomials. This is completely known, completely known. And this for unknowns. So originally, I was trying to find W star. And to do that, I have to solve the differential equation of equilibrium for the plate. Do you remember the equation, the equilibrium equation for the plate in bending, plate bending, people? Does anybody remember the equation? Come on. Come on, somebody. The equation of equilibrium of a plate. People, come on. D nabla for W equal P of X and Y. Remember? What was the value of D? Somebody, anybody? D equal to what? Anybody? D, the constant D. No, okay. But yeah, that's
cube over 12.
Exactly. So that's the equation that you have to solve if you want to find the exact solution of this problem. And instead of that, what we do is we do an approximation. This is not exact, okay? And I have to insist before leaving this is that how close we are to the exact solution, that depends on the interpolation. These interpolation polynomials are fixed. When you use a program, you cannot change this. What you can change is the number of joints, but these polynomials you cannot change. So you have to have that in your mind. If you expect a function which varies a lot in certain area, that means that if you try to get close to that curve, you have to use small elements. Okay? Okay.
I have a question.
Yeah.
My name is Ayo. In this part, we can say the same that in the previous that is not the dimension of the elements is not necessary to be the same.
Exactly. Exactly. And even in the case of plates, okay, many years ago, probably 92 or something like that, we started working with this in our faculty. And in that case, for example, we were trying to analyze the structure of a fishing vessel. Let's suppose this is the deck, okay? And we have the deck frames like this. These are the deck frames. Okay, so we decided we are going to discretize like this. So in every point in this partition, we have a joint like this. What happens with this? What shape does this element has?
Like triangular?
Exactly. It's funny, but in that time, the program that we were using, it was named SAP 80, because it was developed in the 80s. And the element that they have available in their library was only with 4 joints. So what we have to do is we have to simply model like this, leave this as an empty space, and we go on like this, and like this. Because we couldn't model this part. Now we have triangles and we have also these elements. They do not need to be rectangular. Okay, but yeah. Did I answer your concern, your question, Sayo?
Yes, doctor.
Okay, no problem. Okay, so let's say now a couple of words about modeling, okay? Which is something which is, I think it's, okay? We are never able to solve an exact structure. Why not? Because there are so many difficulties. For example, I give you a plate and you can say, okay, now we consider that the plate has constant thickness. Does it have really constant thickness? And the answer is no. No. I can give you a thickness gauge and you can check the thickness at different points and the values will be different. Now, what happens is that the differences are very small. So what we can assume is that the thickness is constant, is uniform, but it's not really. Okay? And things like that. So what we are doing really is modeling the plate as a plate with uniform thickness. That's a simplification. Okay? So in general, I can say that we have to simplify an structure to be able to analyze it. For example, if I give you a plate, a real plate with variable thickness, it will take us forever to solve it. It will be extremely long process. So instead of that, what we do is we simplify. And this process of simplification is what we call a model of the structure. Okay? For example, I can give you a ship structure. Probably you have been on board. No, let me use another example that this example probably will remind you of the final evaluation in the ship structure scores. Okay, for example, let's suppose that we have a pedestrian bridge. Remember in your final exam? Like that. If I see from here, I have a plate and I have two longitudinal reinforcement like this. And of course, we have transverse reinforcements below the deck plate like this. So here, this will be your reinforcement, transverse reinforcements. What's the easiest way to see this? We can see that this is very long, right? It's very long compared with the width or the height. So the first thing that I can say is, since it is very long, What do you see if it is very long? How can you simplify it if it is very long? People, tell me. What comes to your mind when you see something which is very long? Immediately.
Maybe it has a symmetry axis.
No, no, very long, very long. See, pay attention to this. From here to here is very large compared with this dimension or this dimension. Since something is very long, what can you see how can you see it in a simplified way?
We can take as a beam.
Exactly, exactamundo. Yes, it's a beam. It is really a beam? No, it's a model. It's a simplification. So, since it is very long, we can analyze it. I'm sorry. We can analyze it as a beam. This is a simplification. It's a model. Okay, so we can say, okay, instead of, this is a 3D structure. Definitely it's a 3D structure. So what we can do is we can say, okay, we're going to take this like this. Let's suppose it's simply supported like this. Now, up here, you can imagine that we have people walking and they're carrying probably load. How can you model the load on this beam?
It can be a distributed load.
Exactly.
Load distribution.
No, it is really uniformly distributed load? No, because you can see here, for example, in this space, in this little space, there is no load. But I don't think, I agree with you, I don't think that will make much of a difference. So what we can say is that we can apply the load as this one. This is uniform. What else? Do you think the section along the length of this bridge, it's uniform? Probably in here, you will increase the material, okay? Because here you will have these supports. Okay, so here you need to do a hole to include a pin in order to support this, the bridge, right? So probably you have to increase the thickness of the material in this area. But here, are we going to? No, forget it. We simply forget about that and we can say that this is the EI is constant. So what can we say? That in order to analyze this pedestrian bridge, we can model as a beam simply supported with uniform load and constant section. Is this really that? No, it's just a model. Okay? That's the idea. You see the structure and you can analyze it in a simplified way. And according to this simplification, the way you model, we can proceed in order to do the discretization. Okay, now the next step is going to be discretization. Since this is a model, I'm sorry, this is a beam, what do we do? Well, we'll simply include joints in order to partition this domain. So we go, let's include 4 elements, 1, 2, 3, and 4. So we have 5 joins. So in this case, we have 5 elements. Okay. Now, let me go back a little bit and let's see more in detail this structure that we want to analyze. If you are stepping, if somebody is stepping, or for example, puts a load in the center in this area, what do you think will happen in this area? There will be probably a local deflection, right? See, this thing here moves downward, but also the plate moves a little bit relative to the side. Can we calculate that with this model? The answer is definitely no. So if we want to analyze with more precise way, what we can do is we can model this structure, consider it as it is formed by pieces of plates. Okay? So this is the first model. It's extremely simple. Let's suppose that we want to go one step further. So let's go here. We say this is the second model, model 2. The bridge is composed of pieces of plate. Okay, now comes the most important part. Okay, let me see. I'm going to show you just a little piece of that. Okay, so we have one plate on the deck. Oh, I'm sorry. Something happened here. Okay, let me go back. Here, I'm sorry. Jesus. There. Okay, now we have plate on the deck, plate on the side, and we have, I'm going to draw here, a transfer reinforcements. Here I have another transfer reinforcement, but it's below the deck plate. There. And now we are considering that each one of these is a piece of plate. Of course, this model, it's much more complex. Immediately you ask, is the thickness uniform? You know that the thickness is not uniform, but we can assume that, for example, on the deck, on the side, and the transfer reinforcements, each one of these plates has uniform thickness. That's a simplification. So assume that each part has uniform thickness. That's a simplification. We can assume also that the material is steel. So this is E, this is nu. People, E and nu. Somebody, the value for E for the steel, anybody? Value of E of the steel, anybody? Value of E for the steel, people, come on.
2.07 for 10
times 10 to the
11 newtons
Okay.
over meter square.
meter square, yes. And how about nu? Anybody remember the value for nu?
0.3.
0.3, exactly. Okay, so now you can see that this is pieces of plates. Now the question is, here I can take a material from here, this point. Okay, I can go to the lab and put it in the test, and I can get a value of E. Now I can go here and I can take a piece of material from this point, and I can do the same, and I am not going to get the same value for E. So this, what I'm saying here, assuming, is a simplification. That's the modeling. Because in general, I can assure you that the thickness is not going to be the same. I can assure you that the mechanical properties of the steel is not going to be the same in each one of these pieces. This is just a model. Okay, and now let's go on. Discretization. How are we going to discretize this? Remember, this is plates, these are plates, and plates have 2 dimensions. So we have to be careful. I'm going to simplify, I'm going to draw just a little bit here. See, for example, this is the transverse. So it is this element. Here, I'm going to have a piece of that. And here, I'm going to have the deck. Now, let's discretize. So I'm going to use a different color here. So I'm going to need joints. So I'm going to partition the deck plate. Jesus, I need colors. Damn it. Anyway, let's partition here. And here we need to partition like this, like this, like this. There. Each one of these rectangles is an element. So in here, I have, for example, 4, 8, 12, 14, 17 joints. And I have 2, 4, 6, 8, 10 elements. So we have 10 elements, and I think I said 17 joints. So this is proportional to the number of unknowns. It's not going to be 17 because this is a 3D problem. But in general, that's the idea. You model. What do we mean by that? That means that we are going to consider the structure in a simplified way. Okay? We have the same structure, and we have seen it in 2 ways. This, like a beam, because it's very long, but we can recognize immediately that we have limitations. We can use this one here, which is more detailed, and still we can see here that if we consider that the thickness is uniform, that's a simplification. If we say that the material in the whole system has these two values constant, that's also simplification. And again, how would you apply the load here? Well, what we can do is, let me see if I can change color, and see if I can change color. I can, for example, I can consider this. This is, for example, half weight of one pedestrian. See, it's like considering that you have somebody stepping here and one step here and one here. And this half weight is applied here. Is this exact? No, it's not. See, all of this is just a simplification. But if we do not do that, that's going to be very difficult, because here the shoe has a certain area. And if we want to represent that in here, we should have a very detailed discretization, and we don't have the time for that. And instead of that, what do? We simply apply it as a concentrated force. That's a simplification. People, do you have any questions about it? Okay. So we're going to go on with the general steps of the finite element method when we return, because I think we need a break. Okay. So let's take a 5-minute break, and when we return, we will go on with the general step of the finite element method. I don't know if we will have time to say a couple of words about bars, and then I will leave 5 minutes for questions about assignment 1. Okay, let's take a break here.